is start talking about a topic called features and matching. And what we're going to look at in this first hour is an application of matching images together around search, particularly this topic of visual search. So I mentioned this briefly in week one. Visual search is the process of searching a data set of images using an image as a query, so searching using images rather than text. And actually this is super relevant to you because this is going to be the topic of your coursework, which is set as of right now, and you can download it from Surrey Learn, so please make sure you do that. That coursework, by the way, I'll say a little bit more about at the end of this session. That's due on the 20th of November. Okay, so the learning outcomes then of this session are, first of all, I'm going to describe this problem of visual search to you, and we'll talk about the problems around visual search, including something called the semantic gap. And I'll explain this term image descriptor to you and how it's important to image search and what desirable properties of image descriptors are. We're then going to look at how we can implement some basic search algorithms based on colour and edge information in an image. And this will form the basis of what you need to do for your coursework. And then finally at the end, we're going to talk about ways to evaluate the performance of a visual search system, which is again something that you'll need to do during your coursework. Okay, so visual search then is this problem of searching a database of images, visual content, using a visual query. Okay, so suppose I have this data set of images here, and this is actually the data set that you're going to be using for your coursework. It's a data set produced by Microsoft. It's got just under 600 images in it. And let's suppose you have this query here of some cows. What you'd expect to see as a result of a visual search is a ranked set of results where the top ranked results are the most relevant and the bottom ranked ones are the least relevant, and you would hope to see some cows, right, in your results. Okay, so this process of visual search is a process then of measuring the distance, the similarity somehow, of this query to every image in your database. So the obvious questions then are, how do we measure the similarity of a pair of images in order to make that search? Everyone happy with this? Yeah? Actually, there's one extra step. We may want to threshold that similarity score as well. So if we've gone through our database, measuring the similarity of our query to every image in that database, we not only want to sort the elements of that database, the records in that database, according to that distance score, that similarity score, but we might also want to create a cutoff or threshold on that score, after which we don't show any more results because they're just too far away from our query. Okay, and yeah, basically we're going to look today at different ways of defining that similarity score. So perhaps the simplest way of defining that similarity score is to compute something called the global colour histogram from the image, and this is really a description of the colour distribution in an image. So if I were to take this image here of the cows, just looking at it, I'd say, well, there's quite a lot of green in that image, quite a bit of black, a little bit of brown, and not much of the other colours. Okay, so that's the kind of description that I'm trying to build mathematically out of that image in order to measure this similarity. So the way we do that is by generalising the concept of a frequency histogram to three-dimensional space, where our three-dimensional space is the amount of red, green, and blue in every pixel. Okay, and what we're going to do, everyone happy with what a frequency histogram is? Maybe I'll just say, so a frequency histogram, you've seen it, I'm sure, 1,000 times. It's where you have a set of bins in your histogram, each being a different category, and then up on the y-axis you have a count of how many times that thing has occurred. So if I surveyed you and said, what's your favourite colour, red, green or blue, and you said, 20 of you said red and 50 of you said green and so on, then I'd build a frequency histogram there with a bar that's 20 high for red and 50 high for blue and so on. We call that a frequency histogram. In that example, it's a 1D histogram, but what we're going to do here is build a frequency histogram in three-dimensional space. Okay. So what I'm going to do is visit every pixel in this image and measure its red, green and blue quantity and represent that as a point in this three-dimensional space. So this is a little bit like what we did last week when we were talking about the sky classifier, right? And having created that distribution of points in that colour space, in that RGB space, what I'm then going to do is quantize that space which means break it up into chunks. So I might, for example, say, okay, that this cube of the space is one chunk, this cube of the space is this, and so on and so on and so on. I can break it up into a bunch of sub-volumes within that space. Everyone following me? Because these axes, let's suppose I normalise these, well, let's not even do that. Let's say every pixel in here is going to have a value between 0 and 255 for red, green and blue. So each of these axes will range from 0 to 255 in this three-dimensional space. So I can find a way of evenly breaking up that volume into sub-volumes, and just for the purposes of illustration, I've imagined it's broken up into 6 sub-volumes here. Yeah? Now, what I'm going to do is count how many pixels of my image fall within each of those sub-volumes. Okay, so it might have, 20 pixels ended up within this first division of the space, this first sub-volume of the space. Maybe 3 ended up here, and 2 ended up here, and so on. Okay? In this way, I've counted how many pixels in this image fall within different regions of the colour space. And then what I can do then is just visit those regions, those sub-volumes in turn, and plot my regular one-dimensional histogram. I can say, well, in bin 1 of this space, sub-volume 1 of this space, I've got so much quantity of pixels, bin 2, 3, 4, all the way up to, in this example, bin 6, because I divided the space into these 6 divisions. And then that now is my frequency histogram that represents the colour distribution of that image. Everyone following? Yeah? Okay, straightforward concept. Now, if I were to then visit each of these bins in turn and look at the heights of the bins, I would get a string of numbers. And actually, I could represent those numbers as a big long vector. In this case, it would be a 6-dimensional vector, a vector that's got 6 elements, where each element is the height of the bin. Okay? And that vector then, that vector quantity, is what we call an image descriptor. Okay? It's like a digital fingerprint you've taken of that image, okay, that somehow characterizes its content. So in this simple example here, we've computed this, what's called global color histogram. It's a color histogram over the whole image, and it's given us, in this simple example, a 6-dimensional descriptor, image descriptor, yeah, that characterizes the content of the color distribution, in this case, of that image. So the takeaway messages are, we quantized the RGB space, we counted up the pixels contributing to each of the bins in our quantization of the space, and then final step is we actually normalize this vector. Okay? So what I would do is I would sum up all of the elements in this vector and then divide each element by that sum. So that gives me a vector quantity here, which is still 6-dimensional, but it's just a normalized vector. So in fact, actually, this is my image descriptor that I tend to use. For reasons we'll come to later, it's useful to normalize image descriptors. Everyone happy with the general idea here? Okay, well, I've distributed to you today a handout that's got some code on it, and that code actually shows you how to take an image and compute this descriptor from an image. It's written in MATLAB, and MATLAB's going to be the language that I get you to do the coursework in. Okay, so let's just talk through what's going on in that bit of code. What we're saying is, let's suppose that we've got a pixel in the image, let's call it P, that has some value RGB, where RG and B are in the range 0 to 255. Okay? What I'm going to do is quantize my color space up, my RGB color space up, into 4 by 4 by 4 bins. Okay, so 64 bins. Yeah? Okay, so this is just the same idea, I'm just doing more bins. Right? Now, a convenient way to do that is to exploit this property of bases of numbers. You know, if I'm counting in decimal, I'm sure you all know that, if I've got a number like 123, 123, okay, that means 1 lot of 100, 2 lots of tens, and 3 lots of units. Yeah. Okay. In other words, it is 1 lot of 10 to the power 2 plus 2 lots of 10 to the power 1 plus 3 lots of 10 to the power 0. Yeah. Everyone knows how to represent number bases. Well, what we're going to do here is create a number-based system, in this case of base 4. Okay, so we're going to boil down this value R and G and B, which are in the range 0 to 255, to a number R prime, G prime and B prime that are in the range 0 to 3 each. Does that make sense? The way we're going to do that is we're going to come up with this number of divisions in our space, which is going to be 4. Let's make a variable called Q, which is 4. I'm going to take this value r in the range 0 to 255, and I'm going to multiply it by q over 256. Yeah? And that's going to, and if I take the floor of that, just the integer components of that number, because that could be a fractional number, real number, then that's going to give me a value in r prime that is an integer in the range 0 to 3. Why am I dividing by 256 and not 255? Because then it's going to make sure it doesn't get onto 4. Yeah? Okay? So can everyone see how r prime, g prime, and b prime are going to take this value r in the range 0 to 255 and transform it into a range 0 to 3? Yeah? Okay? Then, in order to represent then that r prime, g prime, and b prime as a single number, which is going to be an index into my colour histogram, I'm going to use this this trick here, okay? Which is, as I say, instead of interpreting numbers in a decimal form, I'm going to interpret these numbers, these r prime, g prime, and b prime, they should be, in the range 0 to 3, by powers of q, where q is 4. Yeah? So r dash we're going to consider to be like the hundreds, g dash, g prime, whatever you want to call it, is going to be like the tens, b prime is going to be like the units. Okay? So my index into my bin of my histogram, my one-dimensional histogram, which is going to have 64 bins in it, remember, is going to be indexed from bin 0 all the way up to bin 63 by performing this calculation here. Everyone see what's going on here? Yeah? So I'm treating Q as my base, my number system. So that's what that code in that handout's doing. What it's doing is it's visiting every pixel in that image, and it is basically taking that pixel, dividing it by 256 and multiplying it by Q, where Q is 4, and then having got those numbers R dash, G dash, and D and B dash, as I've called them in the code, because I can't use the prime symbol because that means matrix transpose, as we saw last week. Okay, then I'm then performing this calculation to get the index of the bin. And that's going to let me figure out which of those 64 bins in my histogram, every one of those pixels in the image falls into. And I'm just going to count how many times pixels have fallen into those bins to build my histogram. Okay, I'll stop there briefly. Has anyone got any questions about what I've proposed there? Yeah? A way of transforming a colour image into a 64-bin histogram. So in other words, I've transformed the image into a 64-dimensional descriptor. Yeah? Image descriptor. So my bins go all the way from 0 up to, in my example where Q was 4, it was 63. But in general, it would be Q to the 3 minus 1. Q cubed minus 1. Yeah? Right. So that process I've just outlined is the process, I'll say it again, of converting a colour image into a point, into an image descriptor, which is can be considered to be a point in a 64-dimensional space. Yeah? So every image maps to a point in this high-dimensional space where every axis in that space is the amount that was in each of those bins. Yeah? So this image of cows here might map to this point in the space. And these images of cows here might map to these points in the space. Okay? And we would expect images that are similar, specifically images that have a similar colour distribution, similar amount of each colour, to map to similar points in this space. Yeah? If I took an image like this guy here in front of these books, it has very different colour distribution, just obviously by looking at it, than these cows do. Not as much green and so on. So that would map to a point that's very different in that space. Yeah? So this process of calculating an image descriptor is the process of mapping an image to a point in a high-dimensional space. I'll say it again because it's so important. Calculating an image descriptor is the process of mapping an image to a point in a high-dimensional space. Yeah? Okay. So, this process then of visual search is nothing more than calculating the distance between points in that high-dimensional space. If I've got a new image here, this image here might be my query image. Okay? This is the image I'm searching with, my query. And I've already taken every image in my data set and figured out where it lands in this high-dimensional space because I computed that global colour histogram for everything in my database. Then what I need to figure out then is which points in this space are close to the point for my query image. Yeah? So I could measure that using, for example, the Euclidean distance. yeah? The L2 norm. I could calculate the distance between my query image, having computed its global color histogram, to every point in this space that I've computed from every image in my data set. And then the nearest image is going to be my top rank result. My second closest image is going to be my second highest ranking result, and so on. And I can rank results all the way up to the number of elements I have in my database if I want, but in practice I'll probably stop ranking after that distance gets beyond a certain size. Everyone okay with that? Great. Well, that really is all you need to know about visual search. The problem is that I've given you an extremely basic way of calculating an image descriptor that doesn't really work very well. But it's a good starting point. Can anyone give me a suggestion as to why that probably doesn't work very well? Yeah. Yeah, brilliant. Okay, thank you. So if I were to take this image here and jumble up all the pixels, I could take all the pixels from let's take this image. I could jumble up all the pixels from this black cow and make, I don't know, a picture of a smiley face or something like that, yeah? Then that image will still have the same color distribution, but it will be obviously a different semantic context, different meaning to that image. So what that tells us is discarding the spatial relationships between pixels when building an image descriptor is not a good idea. Doesn't give us what's called a discriminative descriptor. The descriptor is not discriminative enough. So what that means is that the global color histogram is maybe a good starting point to start thinking about image search, but actually we need something a little bit more sophisticated in order to do a good job. So the next best thing that we can do is actually compute some average color statistics, but do it within subregions of the image. So what I can do is take an image, like the cows again, and I'm going to divide that image up into equal divisions, into what we call a grid. Okay? And within every cell of the grid, I'm going to compute some aggregate statistic about the colours of the pixels within that grid cell. So I could compute a whole global colour histogram, which would give me a 64-dimensional descriptor for every single cell here. But actually, it turns out that's not a good idea. We'll talk about why not in a minute. What I'm going to do is something a bit more basic. I'm just going to look at all the pixels in this cell and just compute their average RGB value. Yeah? So I'm going to look at all the pixels within this region here, and I'm just going to figure out what the average amount of red, green, and blue is across those pixels, and then that will give me a three-dimensional quantity for that cell, a value for average red, average green, average blue, which I could write in a column form as a three-dimensional vector. Yeah? But I'm going to do that for every grid cell in the image. And then I'm going to compute my entire image descriptor for the image by concatenating all of those vectors into a big long vector. So in this case, I've got, for every cell, I've got like three numbers. But then in this example, I've got 8 by 6. So I've got 48 cells, 3 numbers. So I've got 48 times 3 dimensions in my image descriptor. So I've got more dimensions now. But it's more discriminative because we can see now that if I were to take my pixels of my cow and start rearranging them to elsewhere in the image, then that's going to affect the outcome of this descriptor now, whereas it didn't before. Yeah. Well, in this case, what we're doing is we're dividing the image up into an equal number of grid cells. So even if the image is very small or very large, you still get the same number of divisions. So you're still calculating 48 averages. Yeah. Yeah, so I think, so your question is, what happens if the cows shift a little bit? Okay, well, yeah, that's going to give you a very different value. So, so indeed, this is still not an ideal descriptor in those situations. So we're sort of building up to more and more sophisticated descriptors as I go through the lecture. But this, or lectures, I should say. So this is, if we were to take those cows and shift them in the image, what we call translate them in the image, okay, then that would cause a change in the descriptor. So we would say that this descriptor is not translation invariant, okay, it's sensitive to translation. So we'll come back to this idea of translation invariance and also rotation and scale invariance as we talk through more sophisticated forms of image descriptor. But does everyone get the basic idea here, yeah? I mean, one other important consideration is is like what granularity to split the image up into. You know, how fine a grained grid should we use here? So let's come back to that. But you know, at this point, it's worth just pointing out a couple of really important properties of descriptors. Okay, we've already talked about how a descriptor should be discriminative. Okay, so given two images of different content, we would hope to generate two very different descriptors. But giving two images of the same content, we'd hope to generate two similar descriptors. Yeah? So we would want our descriptors to be discriminative as possible, but we also want our descriptors to be as compact as possible, which basically means we want them to have as fewer dimensions as possible. Okay? So in that example of the global color histogram, we had quite a compact descriptor there. It was only 64 dimensions, but it wasn't very discriminative. In the case of our grid, we got a much longer descriptor. It's not as compact, but it's more discriminative. Now, what we could do ultimately is we could take a grid and we could do a super fine grid. I mean, in the limit, every pixel could be a grid cell if we do it that fine grain. You know, divide the image up in that fine grain away. That would give us a descriptor that's really, really long, so it's not very compact. So we need to kind of figure out just empirically what the trade-off is between that level of discrimination in terms of the content that the descriptor can discriminate between and the compactness of the descriptor. You want to use as few dimensions as possible to get as much discrimination as possible. Okay, everyone happy with that? All right. So, but then, you know, all I've changed here in this scenario is the method for mapping an image to a point in the high-dimensional space, which, as I said, is the kind of crux of the whole of the visual search problem. Once I've done that, then my process of measuring the L2 norm between my query and everything in my data set is just exactly the same. So what I've done here is I've taken my general framework for doing visual search and I've substituted in a different image descriptor, one that's better, basically, yeah, performs better. So actually your coursework is going to be all about taking a general framework for visual search, which I'll actually give you the code for, and then implementing different image descriptors and plugging them into your system to figure out which ones perform better on that data set of 600 images from Microsoft. So what sort of results do I get then from this spatial gridded descriptor, as we call it, this spatial grid descriptor? Well, if I were to take an image at random from my data set and submit it as the query, I mean, what I would hope is, you know, the first result I get back, I mean, unless you've got a bug in your code, it's going to be the query image, right? Because the distance is going to be 0, okay, between the descriptor you computed of that image as a query and the descriptor you computed from the data set. But then subsequent images we hope would also contain similar content. So in this example here, we've got a plane. I mean, although the first couple of results are not so great, you know, majority of results we get back then are of planes. Car, not too bad. Sheep, pretty good. Yeah, we'll come back later to how we can actually quantify how well this is performing rather than me just looking at it going, well, it's pretty good. Okay, that's what we call valuation. We'll come to that later. But you can see that it's doing a reasonable job, but not great job on that data set, this color grid descriptor. So, so coming back to this idea that a descriptor should be discriminative, but it should also be compact. One thing that we can look at is whether we're actually making use of all of those dimensions in our descriptor. So in this case, we had 48 times 3 dimensional descriptor, quite high dimensional descriptor. Is it really the case that our data in our data set that we're searching actually exhibits 48 times 3 degrees of freedom? Well, there's a way we can find out. Who remembers what that would be? Right, so this principal component analysis, this building of an eigenmodel we talked about last week. If you remember, looking at the distribution of eigenvalues we get from computing PCA on some data tells us how many degrees of freedom exist within a space. Remember, we talked about how we've got a 3-dimensional space here in this room. We've got a 2-dimensional tabletop here with points distributed all over the top. If we were to take, if we were computing PCA on those points, building an eigenmodel, in other words, of those points, then we would see that only 2 of the 3 eigenvalues are greater than 0 because there's only variation on a 2-dimensional plane embedded within this 3-dimensional world. Well, we can do the same thing with our distribution of descriptors calculated from our images. We could take our image data set, which, as I say, is just under 600 images, and we we could calculate a descriptor, which in this example is just 48 dimensional, and we could imagine we got this variable here, all feet, which contains these features. So this is 591 columns, each of which is 48 rows long. Okay, and we can build an eigenmodel from it. So I provided you with the base code a little function called eigenbuild, which builds an eigenmodel, calculates that mu, u, and v, to save you having to code it yourself for this coursework. If I were to calculate that eigenmodel and then look at the eigenvalues, we'd see in this example that actually only 3 of the eigenvalues here are non-zero. So this tells us that with this example descriptor here, that there's only 3 degrees of freedom in this data. Okay, so what that means then is that we could do what's called deflate that space, or project that space into a lower dimension, those points into a lower dimensional space that retain all of the variation of those points, but doesn't have as many dimensions. So if you remember, this is the process of taking that matrix of eigenvectors, where each column is an eigenvector, and discarding all of the columns in there that have corresponding eigenvalues that are 0 or close to 0. And that allows us to then project that data, in this case 48-dimensional space, down into a space that has only 3 dimensions. Yeah? You don't lose any information doing that because there is no variation in those degrees of freedom. But what you do get is the same information represented in a lower dimensional space. Okay. So this is a plot actually of those points under that particular descriptor. You can see there's quite a large eigenvalue and 2 quite small eigenvalues. So you can see that distribution spread out here. So visualizing that distribution of those image descriptors we calculated from the image is a great way to figure out how much variation we have in our data, and therefore how much redundancy there is in the dimensionality of our image descriptor. So we could take that into account by using a modified version of our distance function. So previously, as I described it to you, I described use of the Euclidean distance, or L2 norm, to calculate the distance between a query image and each of the database images in here. Let's call the query image Q, and one of these images in our database, doesn't matter which one, call it T, so it's the image we're testing against. Okay. What I'm going to do, to calculate the Euclidean distance, is I'm just going to take the difference in the first dimension, the second dimension, the third dimension of this space, square all those differences, add them up and square root them. That's how we calculate the L2 norm, right? The Euclidean distance. Okay. Well, what if, instead of doing that, each time I divide that squared difference in that dimension by the eigenvalue associated with that dimension, of that lower dimensional space I projected the data into. That's going to compensate then for the difference in variation in each of those axes. Yeah? So this modified distance here actually looks a little bit like the Mahalanobis distance, doesn't it? Because what I'm doing is differencing but normalizing by scaling by 1 over the eigenvalue in each of these spaces. Yeah? And if I do that, I end up getting much better performance in my system. So if I take a query image here of my bench, then get a few benches, sheep, some more sheep, and so on. Flowers pretty good. Yeah, okay. So one quite important point to raise about this is that if I had projected my data from its high dimensional space down into a low dimensional space, but then in that lower dimensional space just computed the Euclidean distance, I'd have got no different result at all. Okay, because all I've done is taken that data in a high dimensional space, represented it in a lower dimensional space without losing any information, and that low dimensional space is just effectively a rotation of that data. So the distances between points is going to be exactly the same, yeah? But by dividing through by the eigenvalue, I've normalized that distribution whilst calculating the distance in order to compensate for the variation that's different in each of those directions of variation in the space. So this is the results then of that color grid approach, but using Mahalanobis distance rather than Euclidean distance to calculate it. Sometimes when we do this coursework, because people try and do this, people get very confused talking about Mahalanobis distance because they start thinking about classification and I'm building an eigenmodel and taking a point and trying to figure out the Mahalanobis distance from a distribution. That's not what we're doing here. It's just a different way of calculating Euclidean distance that's normalizing against the eigenvalues. Yeah? Has anyone got any questions on that at all? Okay. Okay, so we looked then at that color gridding example, and we saw that it did better, at least qualitatively, than the global color histogram. But actually, there is another way we can go about computing descriptors that, rather than taking into account the color in the image, it takes into account the texture in the image, okay, which is basically the edge structures in the image. We call that texture in computer vision. If I were to show you these two images here, well, if I were to show you this image, you'd say, oh, well, that's a buttercup type of flower in the UK. Okay? If I showed you this picture here, you'd probably still say it's a buttercup, but there's no colour information in this image. So clearly for you to figure out what's in that image, the colour wasn't important at all. So it might make sense then to explore image descriptors that take into account this relative edge structure in the image, the texture, rather than the colour. And one way we can do that is by using these two filters that we encountered before, the Sobel filters, to extract the edge information from an image. So if I take this image here in colour, turn it into a grayscale image, okay, and then I run over that image my remember when we're talking about filtering image, we consider this to be a function f of xy. If I want to calculate delta f delta x, the first derivative of that image in the x direction, remember I use this filter, which smooths in one direction and differentiates in the other, the Sobel filter, and this image here, this filter here, which does the same for df dy. Yeah? This gives me two fields I compute from this, and I'm sure you remember again from the first week, we can calculate the strength of each pixel's edge magnitude by taking the response to delta f delta x squared plus delta f delta, that should be a y squared, and square rooting it, that gives us our magnitude. But we can also calculate the arc tangent, the inverse tangent of delta f delta y over delta f delta x to get the edge orientation. So what I've visualized here, in this image here, is actually this field, theta, the edge orientation, where 0 is 0 radians, and it goes all the way up to 2 pi radians, which is white. Okay, so the grayscale value associated with every pixel here is basically the orientation of the edge associated with that pixel. Does that make sense? Yeah? So let's, okay, before we move on, let's just take a quick look at some of the areas of this field. It's quite interesting. If we look at this region of the image here, which is flat, we'll see that actually the corresponding image region of the edge orientation image is quite speckly. It's just noise. Because there's no edge information here, the gradients, the image gradients in this area of the image are just noise, and therefore the orientation comes out as effectively undefined. But around areas of strong edge information, we get quite strong repeated numbers that make sense to us. So, grey goes to black, goes to white, as we go around the circle, for example. So, we can use this information to compute a similar descriptor that we had for the colour, the gridded colour image descriptor. But instead of doing a spatial grid of colour, we're going to do a spatial grid of edge information. So we're going to grid our image into regular divisions just like before. But within each cell, we're going to calculate a histogram, okay? And that histogram is going to be what we call an edge orientation histogram. We're going to divide that range of values that pixel can take from 0 all the way around to 2 pi, or 360 degrees if you prefer, into 8 equal bins. And then, this value, this pixel might be, equivalent to 30 degrees, so it might fall into, say, this bin. Okay, so that will be +1 for this bin here. Then maybe the next pixel is +1 for the third bin, and so on. And by the time we visited all of the pixels here in this cell, we've computed a histogram, okay, which somehow represents the contents of the image structure within that cell. Does that make sense? Yeah? But what we did observe before is this region of the image here where there was no real edge information, no edge strength, just ends up being noise, and that's not going to help us calculate a robust descriptor. So actually what we're going to do is, instead of including every pixel in this cell into our edge orientation histogram, we're only going to include contributions from the pixels that have a high edge strength, an edge strength greater than some threshold. That means all of this junk here isn't going to get included in our histogram. Yeah? All right. So what that means is, for every cell in our grid, we've got 8 numbers. So in this case then, the total image descriptor we get by concatenating the vectors from each of those cells is going to be 8 times 6 cells again, so 48 cells times 8 dimensions. Yeah? It's going to be a longer descriptor. The other thing we have to remember to do is normalize this histogram for every cell before we incorporate it within this big long concatenated image descriptor. Why do we need to do that? Suggestions? Any ideas why we need to normalize that histogram? Remember, normalize the histogram means sum up the bins and divide every bin by that sum. Why do we want to do that? Okay, well, it's because we're deciding on every pixel whether it should be included in the histogram or not based on its edge strength. A different number of pixels will contribute to that histogram for each cell, potentially. Okay? So by normalizing, that means that the area under that histogram might be very different for every cell. If we included every pixel and every cell making that histogram, then the sum of those bins would be the same, right? But it won't be because we're doing this thresholding on the inclusion. So normalizing then normalizes against the fact that different amounts of contribution will be made for each cell. So we're normalizing against that number of pixels that's contributed. Okay, so now, if I use that 48 times 8 dimensional descriptor and did my Euclidean distance just like before in my high dimensional space, because remember, visual search is basically about measuring distance in a high dimensional space, as we talked about before, then we're going to get results that look a bit like this. Now these are quite interesting results. So I'm querying here with an image of some grass, image of some water, a sheep, a duck, and I'm getting back results that kind of make sense here. I'm getting watery images here, grassy images here, woolly images here, and so on. So we're certainly getting a lot better, each time we look at these results, a lot better than the global colour histogram at least. But maybe we want to incorporate that colour information as well, because it was also quite useful to us. So how about then we create a hybrid descriptor that combines not only this edge orientation histogram, but also the colour information as well for each cell. So now we're going to take our image, grid it into these, in this case, 48 divisions, and then for each cell we're going to calculate its edge orientation histogram and its average colour. And then that means our descriptor, when we concatenate at the end, for every cell, we're going to now have 11 numbers in it, okay? The 8 numbers from the edge orientation histogram and the 3 numbers from the average colour. And then we're going to concatenate that, so now we've got 48 times 11 entries in our image descriptor. So it's a high dimensional descriptor still. That's a kind of spatial gridding approach that's a hybrid between texture and colour information, which is, for this lecture, about the best performance one we're going to be looking at. Okay, everyone happy with that? Think you could implement that? Great. Here's the results. So now they're really good now. So look at what we're getting back for our cars, our streets, our benches, our water scenes. Okay. So when we talk about visual search now, moving away a little bit from the algorithms to just talking more generally about it, we talk about something called the semantic gap, which is the gap between a human's definition of similarity in an image and a machine computable difference or similarity between two images. So what we're really talking about at the moment in terms of the semantic gap is a similarity that's being measured using low-level features computable from the image, in this case colour or texture similarity. And we're hoping that differences or similarities in those low-level features correspond to our human perception of what is different in an image. But, it's not really going to be necessarily the case. Imagine that I have a cow that is, has some particular kind of texture on it that wasn't typical to my training data, then I would perhaps consider that to be not a cow under this definition. So if I wanted to talk about the similarity of images not based on their low-level texture or color properties, but based on the actual objects present in the image, then we would consider that to be what's called like a level 2 similarity. So we consider images that have similar semantic content, similar objects in them, to be similar. And then we also talk about something called level 3, where we look at high-level concepts. So if an image was happy or gloomy or violent or funny or something like that, then we might consider the similarity of what we call level 3. It's quite interesting. Only kind of about 7 or 8 years ago, this was almost impossible to do with computer vision, but now with deep learning techniques, this is very, very achievable. So anyway, this gap between what computer vision is the operations the computer vision algorithm is performing on your image versus your conceptual similarity as a user is what we call the semantic gap. Sometimes we refer, by the way, to visual search. Visual search is like a modern term, but sometimes in some of the papers you read, visual search is referred to as a content-based image retrieval, or CBIR system. Okay, so the last but important thing I want to cover in this hour of lectures is how we evaluate a CBIR, or visual search system. So the way we evaluate the performance of a visual search system is not by just looking at some results and saying, oh, they look pretty good, like I have been doing so far in the lecture. It is, in fact, by computing some statistics called precision and recall, and plotting something called a precision recall curve. So the idea is that we identify several images that we use as our query set. This is like our test data for evaluating our system. So, in your coursework, for example, you might obtain a query set, 5 or 6 images. And then what you're going to do is go through the data set of images and mark, so let's say one of my query images is of a cow. You go through your data set and you mark which of those images in the data set are relevant, so basically are cows, and which of them are irrelevant, so like not cows. Okay? And we call that markup of the data set the ground truth annotation. So you're marking up the annotation for that particular query. And you do that actually for several queries. Every query in your data set, you mark up what's relevant or irrelevant in the database with respect to that query. And then you compute for each query these some properties called precision and recall. And you can plot those as a curve or combine them to give an overall single number which characterizes how well your system's performing. So let's talk a little bit about those quantities, precision and recall, for a query. Let's suppose I have a query, which might be this rectangle here, and I have a data set here of things I want to retrieve, which contains rectangles and circles, let's say. Okay? The relevant results in this case are the rectangles, given my query is a rectangle, and the irrelevant results are the circles. So I put R and NR there for relevant and not relevant. Okay? When I run my query, I'm going to be ranking, remember, this set of data in terms of its similarity to the query. Okay? Obviously, in a real visual search system, these are going to be images, but I'm just doing this with little icons to demonstrate the point. Okay? So I'm going to get a ranked ordered list of results. Everything in that data set is going to get ranked. So what I can calculate is, for any particular rank, I can calculate two numbers we call the precision and the recall. The precision is what fraction of the results up to that rank are correct results, are relevant results. So in this example here, at rank 1, the precision at rank 1 is 1, so 100%. Yeah? Because at rank 1, 100% of the results are relevant. If I was computing precision up to rank 2, my precision at rank 2, or sometimes we say precision at n equals 2, because n is the number of results to take into account when computing it. The precision at n equals 2 is 50%, because I've got a relevant and an irrelevant result when I look up to rank number 2. Yeah? At 3, my precision is 66%. At rank 4, my precision is 50%. And so on and so on. So when I compute my precision at rank n, I'm considering all results from best up to, or down to, I suppose we should say, rank n. Everyone happy with that? Precision, that's precision. It's what fraction of the return results are correct or relevant. Recall is what fraction of relevant results in the database have been returned up to that point. So, if I was calculating the recall at rank 1, then it would be 1 over 8. I'm not sure that's quite right. It would be 1 over 8. Okay. Here, my recall is still going to be 1 over 8. Here, my recall now is going to be 2 over 8, or 1/4, and so on and so on. And by the time I get to the end of my ranked list, where n equals the number of elements in my data set, my recall will be 100%. Yeah. Because there's only 8 relevant items in the data set. Recall is how many of the results, so what fraction of relevant results in the data set have been returned up to the rank you're considering. Yeah? So it'll always be over 8 in this example. Okay? So, yeah. Well, what's the use of the rank? That will become clear. So what we do is we can compute precision and recall up to a certain rank, and we can do that for ranks from 1 all the way up to the number of elements in our database. Okay? So that enables us to draw something called a precision recall curve. Okay? And the precision recall curve is a complete characterization of the retrieval performance of the system. We have recall on the x-axis and precision on the y-axis, and at every point we plot on here, and we join them up to make a curve, precision recall curve, every point is a particular rank we've computed the precision recall at. So this might be at 1, this might be at 2, rank n equals 3, n equals 4, n equals 5, all the way up to n equals 591 for your coursework. The shape of that curve characterizes the performance of your system. If that curve tucks into this corner here very tightly, where we've got high precision and high recall, then that is a very good system. Okay, that's a high-performing system. If our performance is more like this, it's a low-performing system. Okay, generally speaking, the area under this curve is proportional to the larger the area under curve, the better the system's performed. And the area under that curve is in fact proportional to a quantity we call the average precision of the system. Okay, so first of all, before I move on to average precision, is everyone happy with that definition of precision and recall and the precision recall curve? Yeah? So I guess the answer to your question is, why do we compute it at different ranks? Well, we need to compute it at different ranks in order to fully characterize the performance of the system. Otherwise, we might have a system that performs very well for the first few results but gives us junk afterwards. May not be as good as a system that performs consistently well across all of the top ranks. Well, there's not. Yeah, so you can compute. So when you do a visual search, let's say in the coursework you've got a data set of 591 images. Okay, you run your query against that data set. What you're doing is ranking those 591 images based on the similarities of the query. So you can only compute your precision and recall up to 591, n equals 591, because nothing else to rank. Yeah. So what criteria do you use in terms of deciding what rank you go up to? You go all the way up to n equals max, where max is the number of elements in your data set. Yeah. Well, yeah. I mean, if you're thinking about cutting off your rank, then yeah, you would cut off a rank where the precision gets below a certain amount. But I mean, you'd have to, I suppose, collect a data set of representative queries and sort of see what would be sensible. I mean, usually, and for your coursework, I wouldn't worry too much about cutting off on the rank. I mean, normally what you would do is just keep showing the user results until they tire of it. I mean, if you go onto Google, I mean, you can keep clicking next almost forever, right? But in practice, users will absorb, at most 1 or 2 pages of search results. So the similar thing can be said for this. Yeah, it's more of a user experience decision than a sort of a computer vision decision. Okay, so this precision recall curve is a complete characterization of the performance. It shows you whether you're performing well for your top ranked results versus your later results, but it's often useful to get a single value that characterizes, quantifies the performance of your system. We call that value the average precision. And the way we calculate it is using this equation here. First of all, we figure out how many documents in the database, or how many records in the database are relevant to your query. So in my previous example, it was 8 for that rectangle. Okay? And then what we do is we go through from n equals 1 all the way up to m, where m is our maximum rank. So in the example I gave you there, 591 for your coursework. Okay? And then what we do is we multiply the precision at n, at rank n, with basically a number 0 or 1, which is 0 if that particular value at rank, that particular record at rank n is relevant, and is irrelevant. And, sorry, let me say that again. This is like a binary function that gives you 0 or 1. If the result at n, at rank n, is irrelevant, then this function gives you 0. Otherwise, it gives you 1. It's relevant. Okay. In other words, what you're doing is you're going through the rank list of results, summing up the precision at n for all of the relevant results, and then dividing by the number of relevant documents. That has the effect of giving you a number that is guaranteed to lie between 0 and 1, okay? Where 1 is the maximum average precision. So that'd be like a perfect system, and 0 is awful. Yeah. 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 Okay, so first of all, that's a really great question because it points out something I perhaps should say as well, which is for every query, you get a curve. So if you've got a set of queries, images, which you should do for your coursework, you should produce a set of curves, or equivalently, you could average them together to create an average curve. An excellent PR curve in your coursework would be, a set of queries that spans, maybe 5. I don't want you to spend too much time on it. So, ideally you'd have a query for every class, but in reality, maybe just do like 5 queries, one for each distinctly different kind of image, and then you would then have on the same axes those curves for each of those queries, and maybe like an average curve, and that would show you the relative performance of the system at retrieving cows versus, say, I don't know, people. And similarly, you get an AP score for every query. You can average them together to get like an average precision, which would give you which we call the mean average precision, remember, which is characterizing the performance of your system, but for all queries. Another way you could go about evaluating a retrieval system, although I don't encourage it for this coursework, is to consider the semantic or level 2 similarity in terms of this semantic gap. So if you query with a cow, you would expect cows to be returned. You could consider that to be almost like a classifier. Yeah, you're looking at the for a result and saying, is that a cow? Is it not a cow? And you're making a kind of binary decision as to whether it's correct or not. And then you can incorporate that into a confusion matrix. So for a given query, how many cows, sheep, bikes, and so on is it returning? This is not as descriptive a way as producing a precision recall curve, and I wouldn't encourage it, but it's just to point out that you could consider it in that sense. So, okay, so in summary then, in this hour, I've described this problem of visual search to you and the related consideration of the semantic gap. I've explained what this term image descriptor means. It's this way of converting an image into a point in a high-dimensional space for the purposes of visual search. And we've talked about desirable properties of image descriptors, that they must be discriminative but also compact. We've looked at how we can implement some basic visual search algorithms, but there's a lot of space to explore there. We looked at several image descriptors that you could try out in your coursework. In all of the examples I've given you, we've looked at the Euclidean distance and also the Mahalanobis distance, but you could look at other things. You could look at L1 norm, for example, and see what effect the distance measure has. And we also looked finally at a evaluation methodology for figuring out how well a visual search system is performing. Okay. And there's a little bit of further reading on this, but it doesn't really go into an awful lot of detail, being honest. It's more relevant for the next lecture. Okay, well, that's the end of this lecture. Just reiterating the point about the coursework then. So the coursework for this module is to build a visual search system, basically implementing the techniques in this lecture. there'll be lab support for that, and in fact the lab this week will be about getting you started with some skeleton code that I've produced for this visual search system. So I supply you with some skeleton code in MATLAB. It contains a function called visual search, CVPR visual search, which is the basic framework for doing visual search. This framework will go through all of the images in the data set and call a function compute descriptor in order to compute a descriptor from it. And then it will then go through and call a function which is like compute distance or something like that to calculate the distance between two descriptors. Now, in the form I've given it to you, the compute feature function just returns random numbers, so it's useless as an image descriptor. And the compute distance function doesn't do anything sensible either. So it's down to you in this coursework to implement different descriptors to plug in to those and different distance functions to plug into those functions. Okay, and feel free to modify the rest of the code as well. As I say, that coursework is to be done in MATLAB in your own time, but the labs are there to support you, particularly this one this week. And also, the submission for the coursework is a short report of no more than 10 pages, as well as the code. Please don't include the data set. I don't need 100 copies of that data set. It's quite large. And hand in your code, hand in the report as PDF, and it needs to be in by 4 p.m. on the 20th of November on Surrey Learn is the submission, it's electronic submission. Has anyone got any questions about that at all? Okay. Oh, yes.
The data set, has it already been tagged?
Right. Great question. So the data set is a data set that Microsoft have produced. It actually comes as a set of JPEG files, but the file names, they all start like 1 underscore and then some number, 2 underscore some number, and those numbers go from 1 all the way up to, I think it's 22. So from the file name, you can check. I can't remember what the mapping is, but 1 might be cows, 2 might be people, and so on. So you can use the file name as a way of creating that ground truth to do the evaluation, rather than actually, I don't expect you to go through and manually tag all the images. Yeah. Any other questions? Okay, well, let's have a break now until 5 past. It's a 7-minute break, and let's reconvene at 5 past for the next session. So, thanks very much.